Professor Carlos Plain of Durham School asserts, without a doubt, I devoted my entire existence to developing a specific theory about the universe, and now that theory is being tested. I welcome this because that's how we move forward. That's how progress is made in science. The James Webb Space Telescope is challenging much of what has been considered fact in cosmology. For the new year, another ultra-deep field image reveals that we have made errors in our understanding of cosmology. The telescope, which was intended to reveal the earliest stars of the cosmos, is becoming an adversary of the previous perspective and may introduce an entirely new form of science. Not all scientists are shrinking in fear from these new findings. Many experts embrace these developments, as it has long been apparent that something was wrong with our old theories. The discrepancies in the measured rate of the universe's expansion alone should have shaken researchers' awareness long ago. However, instead of interpreting the warnings directly, they adhered to outdated models. The cosmic microwave background radiation, CMB, thought to be the oldest light in the universe, was emitted about 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to form stable hydrogen atoms. Researchers refer to this process as reionization, which made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson while they were working with a novel type of radio antenna technology. This discovery was long regarded as one of the most convincing pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and a prominent place in the history of astronomy. The CMB likely provides a snapshot of the early universe, with minuscule temperature variations offering crucial insights into the conditions shortly after the Big Bang. Scientists used the CMB as a reliable marker for the fundamental parameters of the universe to measure its expansion rate, among other things. The astronomer Edwin Hubble had already determined this in the late 1920s when he found that distant galaxies are receding from us at speeds proportional to their distance. These observations are known as Hubble's law or the Hubble constant. Hubble did not have the advanced measuring tools available many years later when the CMB was discovered, which led to a recalculated expansion rate that was lower than Hubble's original figure. Later scientists recalculated this again, using type Ia supernovae as standard candles, providing stable light that could be used as a reliable measuring reference. The results from the CMB suggested an expansion rate of around 67 kilometers per second per megaparsec, while measurements using supernovae led to a value of approximately 74 kilometers per second per megaparsec. What does this gap in determining the universe's expansion rate truly signify? Did you realize that this inconsistency has been recognized since the 1990s? Since then, researchers have known or suspected that something might be amiss with the analysis of the CMB, the methods of assessment, or the very concept of the universe's expansion. The difference between the measured values of the expansion rate is referred to in science as the SAA strain or Hubble tension. The implications of this discrepancy are profound, suggesting that crucial aspects of how we understand the universe might be flawed. For a long time, scientists were puzzled, but since the launch of the James Webb Space Telescope, JWST, it has provided researchers with extraordinary data that may now help clarify the issue of the universe's expansion rate. Some of these ancient and developed systems, whose formation should theoretically have begun even before the Big Bang, are appending old cosmological ideas. Researchers no longer debate errors or measurement issues. They now discuss it as the greatest crisis in modern astronomy. Not only could the expansion rate be incorrect, but the entire concept of the Big Bang is now being questioned. Images from JWST provide evidence of a universe vastly different from what we once believed. The Hubble tension was the first clue. Experts who still trust the old theories now face a critical dilemma. Do we truly understand much about the universe? Many scientists now stand on the remnants of their once beautiful, though flawed, sources, exploring space with fear while grappling with what they uncover. In light of the crisis in science, we must ask ourselves, what do we really know about the universe? To answer this, we must understand how science operates. Theoretical scientists employ a complex network of mathematical models, accurate data, and logical reasoning to draw conclusions from the general to the specific. Their understanding arises from a combination of observations, experimental results, and speculative hypotheses. The term theory alone suggests that these are constructions and ideas, not absolute truths. The only dependable data we possess are the images captured by telescopes, the sound waves and radiation received by radio telescopes, and the latest data from neutrino detectors or gravitational wave sensors. With the James Webb Space Telescope, we now have a tool capable of breaking down the most ancient light into individual frequencies and analyzing it in remarkable ways. JWST can reveal the composition of galaxies over 13 billion years ago, how much mass they contained, and how many stars were present. It can even recreate the shape and evolutionary path of a galaxy. However, JWST has limitations. It cannot always definitively determine whether we are observing galaxies or black holes with massive accretion disks that shine as brightly as a galaxy. We must confront the reality that our scientific understanding has long accepted too many potential outcomes as facts, dismissing missing alternative explanations. Research has been confident in its accuracy for a long time, but the recent discoveries from JWST offer vital clues to replace old theories with fresh insights. As often happens in science, researchers are now awaiting new discoveries so extraordinary that many experts are struggling to come up with new explanations. These findings are shaking the foundations of physical science, unsettling many researchers. Our current frameworks of physical science are still largely based on the work of Isaac Newton from the 17th century. His laws of motion and gravity were the bedrock of our understanding of the physical world and the universe for centuries. Newton's laws governed the motion of objects under normal conditions and worked flawlessly on Earth. However, in space, his ideas needed expansion, which was largely done by Albert Einstein in the early 20th century. Einstein's groundbreaking theory of relativity, published in 1905, revolutionized our understanding of reality, showing that space and time are interconnected and depend on the observer's motion. His general theory of relativity, published in 1915, extended this idea with mathematical proofs of gravitational anomalies caused by the bending of spacetime by massive objects like stars or galaxies. Einstein's theories were successful in many areas, but he was also aware of their limits. He knew his theories would never fully explain the universe and longed for a unified theory, which he did not achieve. To this day, no other expert has succeeded in creating one. Where is the missing piece? Wouldn't it be fascinating to know where it resides? Michio Kaku, a prominent astrophysicist from the USA, stated in an interview that solving this issue would certainly win a Nobel Prize. So let's investigate whether scientists may have overlooked possible misinterpretations or whether our telescopes are to blame. Dark matter and dark energy are at the forefront of potential causes for the cosmological crisis. Current models of the universe suggest that dark matter and dark energy constitute approximately 95% of the cosmos, yet neither has been directly observed and their true existence has never been confirmed. They may not exist at all, which would require entirely new explanations for the development of the universe and the behavior of galaxies. Alternatively, they may have properties we have yet to understand. One possibility is that the true properties of dark matter and dark energy have evolved over time, potentially revealing some form of intelligence. Gravity is another theory that needs to be tested. This force, causing attraction through mass or the bending of spacetime, has not yet been fully proven. The idea of spacetime bending originates with Einstein and has been confirmed numerous times, but we cannot rule out the possibility that gravity may behave in ways we have yet to comprehend or that another force causes the gravitational attraction between objects. Over time, a number of constants have been established in cosmology and astrophysics, but the study of the universe has always been a journey separate from our ongoing quest for understanding and discovery. From humanity's earliest efforts observing the stars to modern space telescopes probing the far reaches of the universe, each step in theory and observation has uncovered new secrets while challenging established beliefs. The James Webb Space Telescope represents a major leap forward in observational space science, designed to peer deeper into the universe than ever before. One of JWST's primary objectives is to examine the cosmic microwave background, CMB, radiation with unparalleled precision. The CMB, often referred to as the afterglow of the Big Bang, offers a snapshot of the universe as it appeared just 380,000 years after its creation. This residual radiation carries invaluable information about the universe's early conditions, including its temperature variations, which are critical for understanding the formation of galaxies and large-scale structures. The discrepancy in the measured values of the Hubble constant, known as the Hubble tension, has been an ongoing challenge, suggesting a lower expansion rate of the universe. Data from Type Ia supernovae and other cosmological probes yields a higher value. This tension suggests that our current models may be incomplete or that there are fundamental aspects of the universe's expansion that we don't yet fully understand. Beyond the Hubble tension, JWST has the potential to reveal insights into other cosmological mysteries, such as the nature of dark matter and dark energy. These elusive components are thought to constitute most of the universe's mass and energy content, yet their existence is still theoretical. As JWST continues to push the boundaries of space science, it offers the possibility of reshaping our understanding of the cosmos. In conclusion, the James Webb Space Telescope represents a groundbreaking tool in our ongoing quest to unravel the mysteries of the universe. Its capabilities could redefine our understanding of cosmology, compelling us to rethink long-held assumptions and explore new avenues of scientific inquiry. This new era of discovery challenges us to contemplate the vast unknowns of space and the possibility that the universe may be even more intricate than we ever imagined. As the James Webb Space Telescope, JWST, continues its mission, it opens new doors to exploring some of the most fundamental questions in cosmology. Its advanced capabilities provide us with unprecedented views of the early universe, potentially altering our understanding of the cosmos. By examining galaxies, stars, and other celestial objects from billions of years ago, JWST allows us to trace the evolution of these structures and learn more about their formation. This is especially crucial in the context of the Hubble tension and other inconsistencies in current models of the universe's expansion. One of the greatest challenges in modern science is the reconciliation of various astronomical observations with our theoretical models. While JWST brings us closer to solving these puzzles, there is still much we don't know. The search for the elusive dark matter and dark energy continues, and new theories are emerging, offering alternative explanations for the observed phenomena. As JWST uncovers more data, scientists are increasingly questioning the foundations of our previous understanding and re-examining theories that have stood for centuries.